do we know it's ductile or not? Okay, so I'll list down a few materials that are ductile over here in general. So ductile material, okay, are like materials like low carbon steel, sorry, low to medium carbon steel. Which are another typical one, very common one, aluminum, brass, copper, titanium, nickel-based alloy. Okay. So in general, if you were to ask me, can we look at magnitude? Yeah. When the yield stress is much smaller than the ultimate. Okay. If you see a material that the yield is approximately equal to the ultimate strength, most likely this is a brittle material. Okay, most likely. Okay, if you see the ultimate is larger than the yield, yeah, then it is more likely to be what, a ductile material. Okay. So in this course, what is the yield criteria used for? Okay. So the yield criteria, before we go to two types, okay? So the yield criteria is used to determine, okay, it's used to determine the transition between the elastic region to the plastic region. Okay. So for our case, we want the material to stay in the what? Elastic region, right? We don't want it to go into plastic region. Okay. So there are two criteria that will be used, that will be taught. Okay. So there are two types of yield criteria. I mean, commonly used. Yield criteria. And you have seen one in action already, okay? And I will put down here, they are very specific for ductile material. Okay? Then there are two. One is known as the maximum shear stress criteria. Okay. And it's known as Tresca. And I usually, have you guys seen before, as I think I taught you guys before when we were doing 3D mold circle, I like to write Tresca as in a tau, Tresca. Because this tau over here, usually tau, you use that symbol for what? Yield stress, yes or no? Right? So that's how I remember Tresca is based on maximum shear stress criteria. Okay, I used to have very poor memory with all this. Like the periodic table between manganese and magnesium. I don't know which is Mg and which is Mn. It's that bad. Okay, I have really, really bad memory. Okay, not bad memory. I could not be bothered. Okay. So the other one is known as the maximum distortion energy criteria. Okay. And this is known as Vomitis. Vomitis, I just able to remember. I know Tresca is shear, Vomitis, the other one has to be what? Energy based. Okay. Right. So these two criteria are the most commonly used. You look at any design work, okay, we usually use these two criteria. Okay. Now, when to use what? By tomorrow, or no, by Friday, when we finish the lecture, you will be able to see when to use what. Okay. So let's look into this criteria, what they are like. Okay, what are these two criteria? So those of you who are, I think, who are in the management program, I think some of you have done material selection and design. Am I right? Given by any of you have done that course yet? Or those in management, have you seen these two criteria before? Right? Which course is it, Lucas? And what is that course called? Yeah, it's called materials, right? So down here, those that are doing in mechanic or not in management, you have not seen it before. Okay, so I'm going to go over it. So even those with management have done it, let's recall them. Okay, so let's look at the maximum shear stress criteria. So this is what we call Tresca. That's what we call Tresca. And then if we were to write an expression, is tau max is equal to stress U divided by 2. Okay? This is equation number 1, where stress, capital Y, is our U strength. Okay? Now remember, our U strength over here is our principal stress. Remember that, yeah? It's our principal stress. Yeah? Because all our U strength is measured in what? Unidirectional. Okay, we don't go two direction. Okay? So tau max, another expression that you will see, this can be also equal to half of the absolute value of stress max. Okay. And this is our equation number 2. Now, equation number 2 is where when one of the principal stresses is equal to 0, okay, one of the principal stress is equal to 0, and the other, can either be positive or negative. Okay. So what do we mean by that? Okay, so if we were to briefly sketch Mohs circle, this is our normal stress, and this is our shear stress. So this is our normal stress, shear stress, element rotate clockwise, element rotate anti-clockwise. So if one of the principal stress is at stress A, which is equal to 0, and the other one is stress B, okay, which is positive, and this is where when we sketch our circle, right? This is our Mohs circle. So we realize that tau max the distance from here to here is equal to stress B, right, divided by 2, where stress B is also our maximum stress divided by 2. Okay. Now, if it's negative, so I'll draw it negative now. Right. So this is our normal stress. This is our shear stress clockwise, anti-clockwise. Then we have our stress A at 0. Our stress B is at negative. So now we sketch the circle. So I'm going to call this an absolute value of stress max. Right? By right, we should call it stress minimum. Okay? Right? By right, we should call it stress, but we're going to call it absolute value. Okay? So for this case, the formula is still the same. Right? You can see the relationship now. Why they put absolute value. So this is equal to tau max is equal to stress B divided by 2. So it's the absolute value of stress max divided by 2. They put it absolute value because by right, this is what minus is a negative value, isn't it? So where it's absolute, it has no sign. Okay. So there is one set of condition where one of the principal stress is equal to what? 0. Then tau max can also be expressed as half absolute value stress max minus by stress mean. Okay. So this is our equation number 3. So for the third condition that we have seen, or for the third equation, not condition, I do apologize. This is where when the principal stresses positive or negative. So what do I mean by that expression? So going back to mole circle again. So normal stress, our shear stress. So over here, this is our stress A. And then somewhere over here, this is our stress B. Okay. Then we can draw a circle. Right. So we are aware that over here, this is our stress average. So from here to here, this is our stress average. So to find our maximum shear stress, which is this height over here, so tau max is equal to half of stress A or stress B minus by stress A. Okay. So this will be half of maximum minus by minimum. Okay. But as I said, the shear stress, we are only looking for magnitude. Okay, we're not concerned with the direction. So when there's a case, it's half absolute value stress max minus by stress. Okay, I'll stop here today. After that, we are going to continue to look at the operating boundary of the Tresca criteria, and then we're going to do a long example. Okay, that will take us to Friday. I'll see you guys on Friday then. I've posted quiz number 6. Okay, it is due on Sunday.